Okay, so we'll consider the simple problem of describing the movement of a three-dimensional object like a cuboid. Okay, let's fix some axes. X, Y, and then X cross Y. So let's choose it slightly differently. Say X is this way in the plane, and then Z is X cross Y, so it should be upwards. And then let's say that the position of the center of mass is X, Y, Z. And then there's gravity. Okay, so the problem is given an initial position, orientation, and linear / angular velocity. Describe the motion of the object. Okay, so as we've always done in this course, we first derive the equations. We simulate, usually using ODE, and then we animate. Okay, everything is done in Python, not MuJoCo. Okay, so for equations of motion, we'll use Euler-Lagrange method. Okay, so as I said, there are like 3-4 steps. We start with the positions, then compute the Lagrangian, then get the equations. So let's do that. So first is position. And remember, we also need orientation. So the position is X, Y, Z. And for orientation, remember in the past we've used, for example, the angle, right? So here we'll also use the angle. In fact, we'll stick with the Euler angles. And then when we use Euler angles, we have 12 combinations, right? So we can choose any system we want, but we've developed equations for the 3-to-1 system, which is also the ZYX system, where we had angles psi, theta, phi in that order. So let's use that. Okay, so velocities, we have linear, and we need the angular velocity. So the linear velocity is simply x dot, y dot, z dot. Okay, now angular velocity. Remember, we had talked about the rate of change of the Euler angles. So psi dot, theta dot, phi dot. But I told you that those rates are not really the angular velocity of the object. To get the angular velocity, we had to use that equation. If you remember, r dot equals s times r, and that gave us the angular speed. We in fact had two ways of describing the angular velocity. We had angular velocity in world frame, and then we have angular velocity in body frame. Okay, so we have a choice. We can use either of them. Now the choice of what to use will depend on how we want to express the energy of the system. Because remember, the reason why we want to compute the energy is because it goes into the potential and kinetic energy, in fact, the kinetic energy, right? So we will actually use the body frame angular velocities, and I'll tell you why I'm doing that a little bit later, but just trust me for now. We'll only use the angular velocity in body frame. We will not use this. In fact, universally, you'll see that people do not use angular velocity in world frame in the equations. Okay, so this is kind of interesting, and this is something which you want to remember. This is world frame linear velocity. And this is angular velocity in body frame. So we use the world frame linear velocity, but we always use the angular velocity in body frame. So this is the difference you normally see when you talk about motion in 3D versus that in 2D. 2D usually use the angular velocity in world frame. Yeah, and I'll get to that in a bit. So what's the angular velocity in body frame? This is a formula I derived in the class last time. So angular velocity in body frame is given by, so let's say that has 3 components. One, 0, 0, 0 cosine phi should be minus sine theta, cos theta, sine phi, 0 minus sine phi, cos theta, cos phi, and then it multiplies with the Euler angular rates, p dot, theta dot, psi dot. Okay, so I don't know if I skipped this, but what is the angular velocity in body frame? It basically is this. If you have an object, and then let's say that this is x, z, x, y, z. The angular velocity in body frame is the angular velocity with respect to the axes, which are always fixed to the body and move with the body. So the x-axis here will always be pointing in that direction, in the direction I've shown. And as the body rotates, the x-axis will rotate with the body. So the angular velocity in body frame is going to be omega bx, omega by, omega bz. Okay, in other words, the angular velocity in the frame attached to the body and rotating with the body. Okay? On the other hand, if you look at world frames, so let's say that this is the same colors, x, z, okay, so this is the world frame. And the world frame is fixed. So as the body rotates, the world frame doesn't move, but the body frame does move. So the angular velocity of this body in the frame of the world is the world frame velocity. So if you had an angular velocity in the world frame, let's call that wx, wy, omega x, omega y, omega z, it's going to be the angular velocity in this frame. Okay. So no matter how the body moves, the angular velocity is described by those omega x, omega y, omega z. And you can see that clearly as the body rotates, the angular velocities will change because the way the object moves, if the angles made with by the body with the XYZ changes, and so the angular velocity will change. Okay, so that's that. Let's go to the next step. We've defined the position orientation for Euler-Lagrange. Let's define the Lagrangian. For that, I need to compute the potential energy. So second is get the Lagrangian, which is T minus V. So V, which is the easier one, is mg z. I'll just put z because z is the direction in which the gravity acts. And since z defines the global z or world z, I can just put z. And then we have T, which is the kinetic energy, is half m x dot square plus y dot square plus z dot square. Okay, so now I need to write, so there's another piece, which is the kinetic energy due to rotation, right? So for rotation, I actually have two options. I can do omega transpose I omega. Okay, so I is going to be the inertia matrix. Okay, and omega is, well, here I've used omega as omega x, omega y, omega z. So this is the world frame angular velocity. Okay, now the problem is this. If you use this kind of description, you're going to run into issues with this part. This part is the inertia about world frame. Okay, so what's the inertia about world frame? Well, you can go back to this figure. It's the inertia about this frame. So as the object rotates, right, its inertia about the world frame will change. So if the first piece remains the same, the second piece, they'll write it as omega b transpose I b for body frame, omega, where this is going to be now omega bx, omega by, omega bz. And if you choose well, I'll just write the general form. First, it's called this, let's just put it IB like. This should be a B here, and let's call this IB this fashion. So IB11, I12, B. Okay, so this is the inertia. I just put a generic inertia for like a generic non-symmetric body, but then many times if you use symmetric bodies, you'll see that this inertia sometimes boils down to this very simple form. Let's call that I1. Okay, that happens when the object is such that if it's axisymmetric and there is an isotropic, the mass distribution is the same. The inertia actually boils down to a diagonal inertia for something which is symmetric. So, okay, now I've written the inertia about the body frame, which is here, right? So this is the inertia about this x, y, z. So when I rotate the object, the inertia about x is here, will remain here. If you turn it, ix is here, x is here, inertia about x will remain the same. So no matter how you turn this, the inertia about the body frame remains the same. It does not change because it's a property of the body. So when I write the equations in this fashion, okay, I don't need to keep track of the inertia. It's something which I can get it from a CAD file, for example. It will give me the inertia about the body frame. And I can just plug in this equation and go from there instead of trying to use all these rotation matrices to keep track of that. So that's why when people write the second term, they don't write it in world frame. So this practice is not followed. And typically you write it in the body frame because you just have to deal with this nice inertia, which is usually symmetric with only diagonal terms for a symmetric isotropic object. So that's how this comes. And then once you have that, we can then write the equations of motion because now we have both terms. So I'm going to assume that the inertia is actually this I prime, I2 prime, I3 prime, just to make our life easy. So I'll write that Lagrangian now. Is T minus V. So T was half mx dot square plus y dot square plus dot square plus half, let's call it I1. I'm going to skip the 1, just put I1 bar omega bx square plus I2 bar omega by square plus I3 bar omega bz square minus mgy, so mgz. Okay, now that we have both those things, let's write the third piece, which is write the equations using the Euler-Lagrange equations. So this is going to be d dt of dl dq dot minus dl q equals the generalized force of q j. Okay, now in order to cycle through all this, I need to specify what qj is. So qj is going to be x, y, z, and then I have the Euler angles. So theta. So I think phi first, then theta, then psi. So there are 6 degrees of freedom corresponding to 3 linear motions and 3 angular motions. And so there are 6 degrees of freedom. So there will be 6 equations. So I need to take this equation and take the derivative. So there will be 6 equations. And then for the time being, I can just choose qj to be 0. I'm assuming there are no external forces. And so doing this derivation in by hand is cumbersome. So I actually used Python to do it. But what you'll do is you'll see that this is not a problem. But here we have omega bx, omega by, omega bz. And you need to substitute the value of omega bx, y, and z from here. Omega bx, by, bz is in terms of theta dot, p dot, and psi dot. So put that. Then you'll get an expression which will look pretty complicated because now it's going to be have thetas and cosines and sines, and then take the derivative. So I'll show code which will do that. And once you do that, the fourth step would be simplify as a x equals b, like we've always done, where a would be a 6 by 6 matrix, b would be 6 cross 1, x would be a 6 cross 1 of unknowns. And those unknowns are going to be x double dot, y double dot, z double dot, phi double dot, theta double dot, and psi double dot. Okay, so those are my equations of motion involving the accelerations. I integrate them once to get the velocities, second time to get the positions. Once I have the positions, I can make animations. Okay, so here's my code which gets me the equations of motion. So essentially, I showed you ax equals b, and the code produces. Okay, so it produces the 6 by 6 A matrix. You can see it has lots of zeros. Okay, here it starts getting a little bit lengthy. It's the orientation part which gets a bit lengthy. And then the B terms have all these things, so really long. Pretty long. And then it also gives you the rotation matrix, which is associated with that angular velocity to Euler angular rates conversion. And then what I do is I take that and then paste it into my sim falling block where I need the equations of motion to use ODE integrate. Now, this is all copy pasted. Okay, so running this. Okay, so that's the block. Okay, maybe I should slow it down and maybe I should get rid of these other animations. I think I didn't do closer. So I need to set an initial condition. I think let's see. Okay, so this is my initial condition. I randomly set the initial velocity in the z direction to be 5, and then I set some spin velocity, so p dot, theta dot, inside or some random values. And I simulate for 1 second, and I can maybe make it a little bit slower by changing this to 50. Okay, so that's not really very helpful, right? But it basically simulates the system when you put random velocity in flow. Now,